Mel wasn't able to come. Mel wasn't able to come. So I'm here as a poor substitute. Mel was looking at data from years ago, and he's got a reanalysis. So the major topics, he's got an equation which relates the helium-4 that's measured in a mass spectrometer measurement, and it relates to the ratio of the excess power to the current density, or the electrochemical current. This relation is in connection with his experiments, which have some features that are unique. So for example, back in those days, people would oftentimes see excess heat bursts stimulated, for example, by a current ramp or something. So the excess heat as SRI, for example, is very dynamic, whereas in Mel's experiments, the excess heat would tend to be very constant. And so having P excess over I, if the I is constant, P excess is constant, then you can have a ratio which is meaningful. So these relations are for Mel's data sets and may not be applicable to other data sets with more dynamic excess power. So there's two of these things. They're essentially the same thing, but one is interpreting the helium-4 in terms of ratio of power excess over current. The other is relating the excess power over the helium-4 measurement and the current. The fusion, he's thinking about a DD fusion reaction, sort of the old style Fleischmann-Pons, 2 deuterons going to helium-4 with 24 MeV going into energy. His remarks on the importance of grain boundaries, both as locations where the reactions might occur and for the escape of D2 and helium-4 into the region between the grains. In some of his experiments, most of the helium-4 escapes into the palladium. So these relations are derived, assuming that all of it escapes from the palladium. As in his experiments also, in Ed Storm's experiments, the excess heat rate appears to be controlled by diffusion either of helium-4 or deuterons. Finally, oxygen in palladium is not helpful for alien artifacts. So some of you may recall this from 1991 paper. This was one of the first publications where helium correlated with excess energy was described. Fleischmann and Pons had noticed the effect earlier, but didn't discuss it publicly. So Miles' work with Ben Bush was and Legowski was some of the earliest reports of it. That's where we all found out about quantitative correlation between helium and excess heat. So I twisted Mel's arm to include a diagram of the experiment, which is, I think, critical for understanding it. So if you'll humor me, I, as a theorist, will talk a little bit about the experimental setup and how this works and why it's important. So there's a cell here that's electrochemistry is going on. So D2O is being broken up into D2 and H2, D2 and O2. And the D2 and O2 go up and around. Is this showing up? Yes, it's showing up. And under normal conditions, it will go through into the flask. Now the flask is initially filled with helium-3 or helium-4 free nitrogen, dry nitrogen. So that flushes the air out and so forth. And then when the electrochemistry gets going, then D2 and O2 go into the flask, and this cock is open, and it keeps on going through here into a bubbler. So the point of the bubbler is that if the pressure gets too high, so some of the gas goes down here and bubbles out. He's able to, the amount of D2O that's D2 and O2, which is produced, can replace all of the nitrogen that's in the flask, something in the order of 19 times in the course of a day. So when he runs this, typically he would run 2 days of flushing out the nitrogen to get a good D2 and O2 sample in here. Then when he's satisfied with it, and hopefully if excess heat is produced, then the stop cocks would be closed off. So then he'd be able to take the flask out, and then the flask could be sent elsewhere. So for example, in one case it'd be sent to Bush and Legowski and colleagues at UT Austin. It would be plugged into their mass spec system. A headache is that the mass of D2 and the mass of helium-4 are pretty close to one another. And so if you have a lot of D2 in your system and a small amount of helium-4 in the system, you're going to have trouble measuring it. So there's activated charcoal in liquid nitrogen that the gas passes through to remove oxygen, to remove D2, and then goes through a second activated charcoal at low temperature to take out any remaining D2 that might be there. So what goes on to the mass spectrometer is largely helium, so that helps the signal to noise ratio. Okay, so I twisted Mel's arm to have some of the data come first, so you can get an idea of what's going on. So here's a sampling of data. So here's experiments run at 2 different currents. And here's excess power that was measured by Mel at the time. The calorimetric accuracy, about 10 milliwatts. So the top one's fair amount of excess power, well above the accuracy. The lower ones are going to be plagued more with signal to noise ratio. In this case, the flask was sent to Rockwell, and also Brian Oliver. So Brian Oliver. Okay, I don't recall if Brian Oliver was at Rockwell at the time. Does somebody know? Okay. Anyway, Brian Oliver was the ace skeptical fellow who could do extremely good helium-4 measurements. So, for example, the accuracy of his measurements were 10 to the 12th helium-4 atoms. So, if Mel's samples had on the order of 10 to the 14th, 1.34, 10 to the 14th. So this is very large in comparison with the accuracy of Brian Oliver's system. And there's some parts per billion measurements here. So that the basic idea is that the current is constant at these levels. The excess power that the cell would produce would be constant over the time where the D2 and O2 would go into the flask, and the measurement would, the flask would be disconnected from the experiment and sent for analysis. Okay, derivation of the main equation. Let me try to make it simple. If you've got excess heat, and if you're making helium, the D2 to helium-4 reaction, then you get 2.6 times 10 to the 11th helium-4 atoms per joule produced. So that's the R1. So that's half of what's going on. The other half basically says if you put a coulomb of electrochemical current, time integrated current into the system, you will get a certain amount of D2 and O2. So R2 basically says that if you leave the current on for a certain amount of time, this R2 will tell you how much D2 and O2 you got. So now if you make the ratio of these two reaction constants, then you get the helium-4 produced per unit energy, and here you get the D2 plus O2 produced per unit charge. So if you make the ratio of this thing, you get a number at about 56 parts per billion. This is helium-4 per watt, and this is D2 plus O2 per amp. So when Mel Miles puts D2 plus O2, he knows perfectly well that there's 2 D2s and 1 O2. So when he writes this, he means all of the oxygen and deuterium, sort of independent of what the ratio is in terms of moles. So as a result, you can get the ratio of the helium-4 to the D2 plus O2, and it's going to be the ratio R1 over R2 times the excess power over the current, or his new constant R, which includes both of them. So his basic relationship is helium-4 is 55.9 in parts per billion times px over I. Now again, this is to be understood that in the flask, all the nitrogen is gone. So there's only D2 plus O2 plus a little tiny bit of helium. So the parts per billion is helium-4 relative to the amount of D2 and O2 molecules. This derivation assumes that all the helium-4 leaves the cathode. And as we will see, that wasn't the case in all of the experiments. So let's go back to some of the experimental results and compare them with his theory, his equation. So if you use the equation to say, here's how much helium-4 you would expect in parts per billion, given a fixed current and a fixed excess power, then here we have fixed currents, we have fixed excess powers. We have experimental helium-4 in parts per billion. And here we've got the theoretical amount of helium-4 in parts per billion. And I draw attention to the topmost number where the excess power was the largest, so the associated fractional errors are minimized here, and where the PPB measurements are presumed to be very good, because this is Brian Oliver's setup. Down here, the argument is reversed. Now we use the formula as a theoretical predictor of excess power, given a helium-4 measurement and a current measurement. So here's the current measurement, and the helium-4 measurements are above. Here's the experimental excess power. Here's the theoretical excess power. And again, on the top, he's looking at this and thinking, well, it's close. But then he scratches his head and he remembers back in those days, the calorimetry wasn't done with the work term. So for example, if D2 plus O2 is made at a certain pressure, you take P times dV, and that's work that the outgoing gas does on the gas that's already there to push it out the bubbler. So as a result, that's not causing heat, but it is chewing up some of the energy. So if you correct for that, then the energy would go up. And in this case, if it was back corrected, the 100 milliwatts here would turn into 110 milliwatts and would be in agreement with these theoretical numbers. The lack of agreement with the lower numbers is associated with the calorimetric errors. The signal's not so much large noise in these cases. So Mel is scratching his head, as we all are, as to why measurements done with good statistical significance aren't more respected among the scientific community. And in this particular case, because the Rockwell errors, the Brian Oliver's error in the number of atoms measured with a mass spec is very small, then the signal to noise measurement associated with these numbers is low. And so Mel will calculate 37 sigma The difference between the 100 milliwatt and the 20 milliwatt would be 37 sigma. And similar, also very reasonably large numbers for the other ones as well. And I pulled off of the CERN webpage the statement that 5 sigma is enough to be the gold standard at CERN for particle physics. Okay, so Mel also worked with palladium-boron alloys and palladium-cerium alloys. And so in this case, metal collection flasks were used, and the earlier ones, glass collection flasks were used. And in this paper, he describes the tests that were done to see about helium leaking in and so forth. So in both cases, for the transport, they were able to have confidence that the flasks were helium leak tight under transport. So in the case of the palladium boride experiment, we've got a PXS, we've got a current, so we can get a theoretical ppb number, which is high, and we can get an experimental ppb number, which is much lower. So Mel's looking at this and thinking, aha, not all of the helium is coming out, that the boron is impeding the release of the helium to the gas. And similar effect in the case of palladium-cerium, that you've got current, you've got excess power, so you've got theoretical amount of helium that you would be expecting to measure. You don't see the helium in this case. And so once again, the argument is that the cerium is keeping the Helium-4 from coming out. So here's data. The first one is a palladium-boron sample. So again, the amount we'd expect and the amount was seen is not good agreement. For some of the others, there's better agreement, but probably it's reasonably clear that not all of the helium is coming out. So Mel's scratching his head and looking at papers and talking to Imam. And Imam confirms that in the case of palladium boride, when it gets made, that boron collects preferentially on the grain boundaries and inhibits helium from going from inside the palladium to the grain boundaries. So the idea, here's a plot from Wikipedia page. You've got a grain, you've got the grain boundaries. Helium diffusion in the metal is not all that particularly fast, but once it gets into a region, into a grain boundary region, then you can get orders of magnitude increase in the rate at which the helium goes out. So the basic idea is if you've got some helium and you want to see it, it's got to manage to get to the grain boundary and then out in order to measure. So this is essentially his first few points. Gases and metals escape along grain boundaries. And then according to literature and also according to Iman, then if you add metal to palladium, you're going to get some segregation at the grain boundary, which is going to inhibit the helium going out. You get strengthening by the additives. This has been well known in the field since experience at SRI. The literature, according to Samel, also says that the diffusivity within the grain boundary is hindered when you've got you've got the additives which collect on the boundaries. In uranium, you get H2 and helium escaping along the grain boundaries. And other examples, cerium oxide exhibits a strong blocking effect. Yttrium slows gas diffusivity. I was going to point out that Mel's focus was on the grain boundaries. However, if you think about palladium-deuterium, palladium's got your FCC structure. When you put the boron in, where's the boron go? So most of the boron goes into the O sites. And if it's in the O sites, it's blocking diffusion. So reduce the diffusion of the D and also the helium. It can also substitute for the palladium, but that's less strong an effect. So Mel's thinking about where the reactions occur. So in honor of Ed Storm's contributions, fusion is occurring in certain special locations, the nuclear active environment. For Mel, these include grain boundaries, cracks, and vacancies. And Mel's interested in the possible impact of high electric fields and double layers. Also, in Ed's experiments, in Mel's experiments, I'm not sure how many others, but the rate limiting step for excess heat production is the evenized KT factor associated with deuterium diffusion and helium diffusion. Anyway, there's insights. I will simply summarize. Mel thinks that oxygen is bad for excess heat production. And the cathodes which free of oxygen seem to work. Cathodes with oxygen don't work very well. And summary, which is sort of the same as we began with. Thank you for your attention.
Thank you very much. We are still in time, no problem. Questions?
How about the temperature of the measurements?
Please come to the microphone, okay?
The temperature. What kind of temperature of the experiments?
Is it a little bit above room temperature?
Hmm?
A little bit above room temperature.
Okay, thanks.
I'm glad you reiterated that point about oxygen at the end there, because I'm in two minds about this, and I'd like you to clarify whether you think that's across the board or just with these gas phase metal systems. Because when we were with Professor Piantelli, he said exactly the same thing with regard to his classic experiment with Sergio Ficcardi, that if you had any form of oxygen in there, it did not work. But I'd like you to address the 1994 R. Sundaresan and J. Bokras in the George Ossawa carbon arc underwater replication, where they only found synthesis of iron when oxygen was dissolved in water, not when they had nitrogen present. And the second case is in our own experiment in 2019, after exposure of a Marsa gas on a 10-yen coin, we saw conversion of oxygen on the copper oxide to sulfur, in which looked like snowballs rolling, consuming the oxygen and synthesizing the sulfur, as if long-lived plasmoids that lived for 2 days, such as those published by Bogdanovich in 2018 at the Moscow Nuclear Physics Institute while doing the work. So I'm concerned that, yes, there are cases where oxygen seems to impede this process, but there are cases which it is essential.
Okay, so from the examples that you've given, I would take a meat cleaver and slice between the solid state ones and then the electrolyte ones. In the solid state, Mel and I were talking about this. So the one simplistic argument is that if you have oxygen in your palladium, the oxygen is going to end up plunking itself down into an octahedral site, and it's not going to want to leave. On the other hand, Lipson and earlier the Japanese fellow who's, I'm getting old, I can't remember his name anymore, but Lipson repeated the Japanese experiment where Yamaguchi, where manganese oxide was produced on the surface. Now, having the oxide layer in the Yamaguchi experiment, Lipson experiment, was very helpful and apparently critical in producing excess heat effects and charged particle effects. And my thinking on those is that having the oxygen there is basically good for lowering the vacancy production energy of the host palladium atom. So having the oxygen there and then having the deuterium or hydrogen in it to make the water reaction and get the oxygen out, when it goes out, it ends up leaving vacancies behind, which I think are good. But that wasn't, in Mel's experience, the oxygen was just in, it wasn't close to the surface, it didn't get out. So it was, the thought is it was just blocking both sites. I think for the high voltage electrolysis experiments, you use the word plasmoids, and I tend to agree with that, and a different mechanism altogether, in my view.
Well, we've had one example today where the oxygen added to the system appeared to make the excess heat greater in John Paul Bavarian's talk, and that's not in the systems that I've talked about.
Right, but I think that's sort of consistent with the Yamaguchi and Lipson kind of thing. That's what I was thinking when John Paul.
Perfect, thank you.
Yeah.
Last question, please.
Yeah, I just had a quick thought. I'm curious what you think about this.
Wait,
I wonder if...
You're Jonah.
Yeah, oh, I'm Jonah. If building off the idea of sort of dopants that would reduce the diffusion of helium when you're trying to do the analysis, I wonder if you could selectively choose other dopants that would preferentially sit at the palladium sites as opposed to the O sites or at the grain boundaries, and I wonder if you would, it would be an interesting control experiment if you didn't see that inhibition of diffusion of the helium-4.
Okay, so there's multiple issues going on. Let's start with the helium diffusion. There was an experiment done in 1977 with helium bouncing off of aluminum, which basically established that the density functional ideas that happened earlier actually held water, that the potential that the helium sees in a metal is linear in the background electron density. So what that means is if you've got materials with high background electron density, like stainless steel, beryllium, that's going to make diffusion of helium very, very difficult. Alternatively, if you have materials that have a low background electron density, then helium's going to have a much easier time going through it. So arranging for helium to get from the grain boundary, from inside the metal to the grain boundary into the region where it can go fast, that's pretty easy. You just want material with low background electron density near the surface. Whether that's compatible with getting any excess heat at all, that's another story.
Thanks,
Okay,
Peter.
thank you. So once again, thank you very much, and maybe very relaxing information that we have, everything, the heat excess you have produced corresponds to the nuclear energy we are expecting, probably. Yeah, so it is not so bad, very good information. But of course, the question is, you have used some normalization factor between experiments and theory, or it was independent, completely calculated from the ab initio, let's say?
No. Mill's argument's really very simple. You know how much energy comes if you have D2 going to helium-4, and you know how much D2 and O2 get made when you've got a Coulomb of charge. And so there's no proportionality factors, there's no adjustable constants or anything.
Okay, thank you very much once again.